All right, 2 minutes, guys. 2 minutes. All right, it's 11. Let's get started. Lord, thank you so much for bringing us together this morning. Thank you for everything that you do for us. Thank you for all the opportunities that this day provides. Pray that you would continue to bless us with everything that we need. Help us to stay focused and to keep our heads in the game. In your name we pray. Amen. All right. All right, so what are we doing today? We're going to recap from last class. We're going to do some more examples, specifically surrounding some of the vector stuff that we ended with yesterday. And then we're going to jump in to some more vector stuff because vectors, right? Vectors. Great. So this is so nothing. Everybody, nobody, most people thought nothing was confusing. So that's great. Let's see what else we got here. Among Us. That would be confusing. I don't believe we talked about Among Us at all the entirety of the class. So for sure, definitely, I would be confused by that. Measurements. Okay. Measurements are the way that, well, no, sorry, measurements. Measure. I'm not sure what I'm confused on that one as well. So we'll circle back later. Sig figs. All right. So in the homework, right, specifically where we need to care about sig figs, right, is and the first answer is chemistry, right? Chemistry is the first place where we really need to care about sig figs because sometimes our reaction components are so small that you really need to make sure that you're able to measure the quantity that you're calculating, right? In this class, sig figs isn't as important because the numbers are going to be pretty big, right? But the textbook, the reason I bring it up is when you do your homework in Pearson, the textbook is expecting you to do it with a certain number of sig figs. There's a couple where it tells you how many it wants, right? So if you're noticing that you keep answering this, like you do the question once, you get it wrong, so you rerun your math and you're still getting it wrong, but you're getting the same number, check to make sure that the number of sig figs that you're using is what the problem is asking for. So how do you know what the problem is asking for? They will either tell you directly, number one, or you have to use the smallest number of sig figs that you are presented with for any quantity in that problem. Okay, cool? Yes, maybe? All right. Slug seconds. Yeah, sure, sure. Um, Professor was confusing. Oh man. Well, I'll work on that. I'll work on that for today. Overall, it seems though like most we're getting the meters cubed, feet cubed thing. I think the important thing is next time we do a big unit conversion, um, think of it as whenever you're doing unit conversions, it's fraction multiplication, right? And so if you have something that is feet cubed and you need to go to meters cubed or whatever it happens to be, right? Maybe it's an area, you have meters squared to square feet, right? Think of it this way. That unit is actually meter times meter, right? And so that's why we have the two conversion factors that get squared, because if we're going to convert 1 meter, we have to convert it a second time, right? Does that make sense? We'll go through it again. It's not the last time we'll see unit conversions for sure. But I just want to make sure everyone's kind of on the same page. I'm going to clear these. Well, before that, I saw parallelogram. Parallelogram is confusing. I would not recommend. 0 out of 10 would not recommend. Okay. Maybe that would be. We'll talk more about some of that stuff in a second when we get into these example problems, right? But before, we're going to do a quick comprehension quiz, right? We'll do this show of hands. Which one of the following is a scalar quantity? All right, is it force, position, mass, or velocity? So if you think it's A, raise your hand. Okay. If you think that it is B, raise your hand. C? All right, and D. Okay. What is a scalar quantity? Let's start there before I share the answer with y'all. I'm sorry, say that one more time. A single number, right? So a vector is what then? Magnitude and direction, right? So something that just has magnitude, right? Does force have a magnitude? Yes, but it also has a direction. Same with position, same with velocity. Mass doesn't have a direction, right? The answer is C. Mass is a scalar, right? Because it doesn't make any sense if I tell you that I have 20 kilograms of mass north. That doesn't make any sense, right? Okay. Here's stuff is still due. Please do the things that are due. Please don't not do the things that are due. Great. If you have any questions on homework, please let me know. But I think today will kind of help shore up some of the, well, obviously it'll get you deeper into the homework items that we didn't cover. This is more chapter 2 stuff today. The unit stuff is like chapter 1. Okay. The Dr. Deism for today. There will be days when you don't feel like showing up, but those are the most important days that you need to show up. Okay. I know. So, right, I know a lot of people don't want to, I know statics class maybe might not be your most exciting part of your day. And for that, I apologize immensely, but it doesn't change the fact that it needs to get done. Okay. So, as Bluey's mom, Chili, would say, boring things are still important. Okay. There you go. All right. Any questions, comments, concerns before we move into some more example problems? Once, twice. All right. Well, then we're going to do this guy. So I am given this tent post here, and I have 3 forces, right? That are 3 concurrent forces acting on the tent post, right? So we're pulling in all 3 directions at the same time. You're given the magnitudes of each of these and the direction, right? So we know quite a bit for this problem, and we're just asked to find the magnitude and the angle of the resultant force, right? So we have to take these and combine them into a resultant. Okay? Pretty straightforward, right? Shouldn't be terribly tricky. It's a little bit different though, right? Because up to this point, we've only been using 2 vectors, and finding the resultant of 2 vectors is pretty simple, right? We break it down into x and y components, and then we add those x and y components. I would argue that this is the same thing with the extra step, right? Now, at what point do we not want to be breaking down vectors by hand anymore? 3 is fine, 4 is okay. I would say 5+ vectors, and you probably want to write a MATLAB script to do this for you, or a code, right? Let the computer do it for you. But that's only as good as our understanding of the process, right? Because unfortunately, things like MATLAB only do the things that we ask them to do. So when we get mad at MATLAB, we are really just mad at ourselves. Okay, great. Anyway, I've stalled long enough. Let's just do the problem. So what's the first thing we're going to do? Well, let's write down these vectors, right? And see if we can put these vectors in Cartesian form to start with. So we'll start with F1, right? So if I have F1 and it's a vector, well, if I write this in Cartesian form, this one's pretty obvious that it is just 300 in the J newtons, right? It's sitting right on the y-axis. The book's not trying to trick you by putting a little angle on it or anything. Direct, right? So that one's done. Great. So we should have no x components for F1. F2 is pretty simple, right? If we wanted to write F2, right? This would be F2 in the x direction, I, plus F2 in the y direction, J, right? So remember, those are magnitudes, the magnitude of F2 in the x direction and the magnitude of F2 in the y direction. And the unit vector takes care of our actual vector portion of that, right? So how do I find F2 in the x direction? What am I going to do? Say that one more time. $450 cosine 45. Does everybody agree with that? So you corrected your answer, but you're also correct. You can do 135 or just be cognizant that you have to throw a negative sign on there. If you took cosine of 135, you'll get a negative of cosine of 45, right? But remember, magnitude and direction. Direction is really important, right? Because if we're going to add these things together, we need to know how much of F2. Is that going to pull us to the left? Is that going to push us to the right, right? So if we're looking just at F, that's not. We're looking at just F2 in the x direction. That's equal to negative 450 cosine. That's awful. Try that one more time. Cosine of 45 degrees. Okay, so what is that? What's that number? It said 0.18, 198. Let's just call it 0.2 for now. And that is Newton. What's F2 in the y direction? Is it the same thing? The sign's gonna be different, right? But yeah, 45 degrees makes this easy, right? We know that the magnitudes have to be the same. We need to double check the direction, right? And you know that the vector is going to the left and up, so that means negative in the x, positive in the y, right? So I'll just write it down here. F2y is equal to 318.2 Newton. So if we write out our Cartesian form vector, we get negative 318.2 in the I plus 318.2 in the J. And that's a 2. So there you go. All right. Put some units on that, right? That should be. So you'll notice that sometimes I will put my units in a square bracket. That is just so I don't get confused. Anything in a square bracket is a unit. You don't have to do that. That's just how I was taught a long time ago. And sometimes when you get hit with a stick enough times, you learn a lesson, right? Sometimes. Sometimes it takes one time to touch the stove, and sometimes it takes more than one time to touch the stove. Anyway, what am I going to do for this third one? This is interesting. I wasn't given an angle. Do I need an angle? Do I need an angle? No. All right, so let's write our F3, right? It takes the same format, F3x, right? I plus F3y in the J. Okay. How do I find F3x? Six hundred times 3/5. It's crazy. That's like, man, that's amazing. It's just dark magic, really. And that's 100%. How did he get 3/5? Yes, but there's something very specific I want you to see relationship-wise here. Right? If you were to write this out, say you had an angle, how would you do it? Say we knew that angle. What would we have? It was cosine, right? What's the cosine of a 3, 4, 5 triangle if we're measuring it the angle from here, right? It's 3/5. We don't need the angle. It's already incorporated into the cosine, right? If you know the lengths, right? If you know the lengths, then you don't need, right? No matter how big that triangle scales, right? That angle will always be the same, right? It could be a 6, 8, 10, right? It could be 300, 400, 500. That angle never is changing. And the ratio between the adjacent and the hypotenuse will always be your cosine, regardless of anything else. All right. So F3 in the X, 3/5 of, jeez, man. So, all right, I want to explain why I am so bad at writing. There's a little button on the side of this pen. And if I hit it, all hell breaks loose in the PowerPoint. Okay. And so I'm trying to be very ginger about not hitting it, but it causes problems. All right, so what's 3/5 of 600? It's like 360. How about in the y direction? How do I get the y component of this? That. I'm going to move that so you guys can see it, actually. Four-fifths, right? We use we use the sign of it. 4/5 of 600, which is equal to 480 Newton. Okay, so, oh, hey, actually didn't do it that way. So what I'm going to do is I'm going to grab my, not that one, I'm going to grab this guy and move it over here move that over there for a second. I'm going to get rid of this work while I'm cleaning this up so we have some room to finish this. Has anybody watched any of the YouTube video, and can you tell me if there's any sound issues or anything? If not, that's fine. Let's write F3. So that should be 360 in the I plus 480 in the J, also Newton. Okay, perfect. So now what? Okay. All right. What do we do now? What do we do now? I want the resultant. How do I find the resultant of this? Yep, add the i's and the j's. So add the i's and the j's. And we're going to use a very creative name, F sub r for resultant. I know, very tricky, very tricky. All right, add up the i's for me. What do I have? 41.8, right? So 360 minus 318 leaves us with 41.8 in the I. What about in the J? What do we have? Hmm? That's a pretty big swing, right? Pretty big swing. But I mean, we don't know how, again, we don't have any context, right? I have no idea how big this tent actually is. Is it a circus tent? Right? I don't know. We just know that these are the forces that we're seeing. So, hey. Okay. But that's not what we were asked for. We were asked for the magnitude and the angle. So how do I find the magnitude of this? Square root of the sum of the squares. I want the magnitude of FR. The square root of the sum of the squares. Good old Pythagoras probably didn't realize how prolific he would be. You know, if he lived today, he would probably be making bank every time everybody used his name. We would copywritten that thing. Been really missed opportunity for him. But all right. All right. 41.8. So all right. So first of all, just looking at this, what are you like how are you expecting this sum of the squares to be closer to 41 or to be closer to 1098? I would hope so. I would certainly hope so. And in fact, it is so close that it is basically 1099. Okay. And that should make a lot of sense because the square of 1098 is much, much larger than the square of 41, right? If that was 4, it would basically just be 1098. There would be no additive thing. Gee. It's a technical term. Don't worry about it. Newton, right? And if we want the angle, how do we find the angle? We're going to call it, I don't know, I'll call it phi to be fancy. Sure. Yep, the tan inverse of the y component divided by the x component, right? So we'll do that. We're going to do it up here. Tan inverse of FRY over FRX, right? There. Move that a little bit. Okay. And if we solve that with our calculators in degrees, and I make sure to put the pen back on, 87.8 degrees. And so we have a resultant vector of 1099 Newton pointed nearly at 90 degrees, pretty close, not exactly, right? So let me do this really quick. I'm going to give myself some space here. We're going to draw it. So I will get rid of this right now. We don't need that. What we do need is this and that. Okay, I'm gonna try. It's gonna let me this time. Say, nope. See, told you. Don't press the buttons. Oh, yeah. All right. So what do we have? Well, F1, right? And this is not drawn to scale, by the way. 100% not drawn to scale. Oh, not drawn to scale. There you go. Let's do this. All right, so here's F1 in the Y direction, right? It's probably a little bit more than I wanted, but that's fine. Then what do we have? Well, we have F2. F2 is is 45 degrees, right? So if we're adding these, we go tip to tail, roughly 45 degrees. And then we've got F3, which is, this one's definitely not going to be a scale because I drew the other ones too big, but here we are. I know. That goes back this way, right? Probably like right there. And so if we're looking at our resultant vector, it would roughly be something like that, right? Which makes sense based on the calculations that we have. And don't worry about these like arrows down here. It's fine. Yeah. There you go. All right. So does that make sense? Everybody cool with how we got there? Yeah. Any questions on this one? No, we good. All right. All right. We got another one. Before we get in there, let's check how you guys are with this concept, right? So if I resolve f along x and y axes, I would like you to take a minute and write that vector in vector form. So you have this vector, and I want you to resolve it into its components. All right. So even if you didn't do the math, right? Let's walk through this, right? Say I'm just looking at this. I'm not going to do the math. Are there any answers that you're immediately going to get rid of? B and D. Why? The Y is not negative. So those are immediately cannot be it. So it has to be either A or C. Okay? So of those two, which one are you guys going with? C, Y, C. There you go. Yep. Because of where the angle is. The angle is off the Y, not off the X. So it flips our sense of cosine and sine, right? So remember, cosine and sine is very much dependent on what angle we're using and where we're measuring it from, right? So always think it through. Always think it through. All right. There you go. There's the green box, so you know it's true, 100%. Can't be lying. You put a green box around it. All right. All right, here's an interesting one. Okay. I want to resolve the horizontal 600-pound force that we see here in figure 212A into components acting along the U and V axes and determine the magnitudes of these components. So let's walk through what this is actually asking us, right? It is saying we need to resolve the 600-pound force. That means what? That means that that is a resultant, right? That is the resultant force. And we're going to resolve it, meaning that we're going to find its components. But instead of finding its components along the X and Y axes, we are using two arbitrary axes, U and V, which are not really arbitrary because they're in line with the arms that split off from this hinge, right? Does everybody see that here? And that, are we good with that? Okay, so this is weird, right? Because how are we supposed to do that? And that it's true. It's kind of a weird one. Very different than the straightforward problems where, hey, here's an angle, break this down to X and Y, right? Okay. So if we need to break this down into components along U and V, that would indicate that we need to have some force along those axes, right? So let's start by drawing a force. All right, so, okay, we've got a force along this axis, right? We have no idea how big it is. And we've got some force going this way. That was a poor choice of color since the other one was blue. Let's try that again. Right? So here's our two forces. We'll call them, I don't know, probably like FU and FV, right? Uh, yep. I know it always gets a laugh for sure. All right, so that's great. We clearly we know the angle for F sub U is 30 degrees off of the 600. You could make an argument, right, that I have a vector, and so I'm allowed to move this vector anywhere along its line of action, right? As long as it passes through that hinge, it doesn't matter where it is. But if you look at it that way, I know that that one's 30 degrees off of U, right? So I can start to build some geometry around that. I, oh, I didn't want to close that. I lost my mouse. There we go. So I'm going to move that guy back to where he was just for a second because we don't have X and Y coordinates, right? So we're going to call these our X and Y right here. Okay. Great. And I think you guys would agree that that kind of makes sense, right? But why would I do that since we don't need Cartesian? Well, I like to frame how I build angles in a 98-degree model because I think this makes it very clear that the angle from that arm right here that is 30 degrees, right? This is 30 degrees. Great. And I press the button. There we go. Why you don't press the button? This is 30 degrees, right? And if I draw a horizontal line down here, you can also see that that's 30 degrees, right? Because of interior angles, because geometry, okay? And this is the part of, well, yesterday I was talking about, I expect you guys to know a little bit about geometry. This is kind of the stuff that we need to brush up on, right? Is how do we determine what these angles are based on the information that we're given? Since this is 90 degrees right here, that means that the angle from the x-axis all the way around has to be 120 degrees, right? Okay. I'm going to leave that there for a minute, and I will advance this slide now. And you can see everything that we just talked about again. right? We found those angles. Now what did we do? Well, we used triangle method. Okay, so if I take this vector FV down here and I move it to the end of FU, right? I get this triangle. You know that the angle between U and V has to be 30 degrees, right? We just talked about that. It's this angle right up here. This angle right here, right? Between U and V, right? And I showed you when we move that up, you can see that that's clearly 30 degrees, right? Okay, great. This is 120. That's the angle between A and V. It's this angle right here. And when we move this up and over, that becomes the angle for the interior part of that triangle. And so now we have this triangle, which is gross because it is not a right triangle. So how am I supposed to find these forces if I don't have a right triangle? Law of sines. So we'll do this now. I will clean this up, right? And we'll zoom in a little bit on there. And we just talked about all this. I think this cleans it up. It's a little bit cleaner than on the previous slide. You can clearly see that this is a 30 degree 120, right? Should always add up to 180 inside of a triangle, right? And in terms of, no, those, there we go. So in terms of our, all right, so this is F sub U, and this is F sub V. All right. And what does law of sines tell us? Law of sines tells us that the sine of an angle divided by the magnitude of the leg across from it has to be equal to the sine of an angle divided by the leg across from it, which is equal to the sine of an angle divided by the leg across from it. And this works for right triangles too. It's kind of trivial at that point, right? Same deal as law of cosines. Law of cosines turns into Pythagorean theorem if you are working at 90 degrees for that angle, right? But this should get us where we want to go. So what is alpha, beta, and gamma, right? Also, if you flip this, if you made it A over the sine of alpha, B over the sine of beta, and C over the sine of gamma, it's the same thing. That doesn't matter. As long as you're consistent with sines being on top and lengths being on the bottom, or lengths being on top and sines being on the bottom, you're all good, right? So in this case, right, we were asked to find the magnitude of these forces, and we have all of the angles, right? So I can say, I don't know, let's start here. Sine of 30 degrees. All right, so here's sine 30. Oh, if I go across from it, the magnitude here is F sub V. And I'm going to set that equal to something that I know, which would be the sine of 30 with this, right? That's our 600 pounds that we started with, right? Yeah. If I algebra for a second, I can solve for FV, right? So bring FV over. Turns out that the signs cancel, right? And so let's do it longhand just as a review for the algebra, right? I would bring FV over. That would give me FV times sine 30 over 600. And then I would multiply by 600 sine of 30 degrees divided by the sine of 30 degrees. Those guys cancel, give me 1, left with 600 pounds. Okay. Makes sense. Everybody good with that so far? Because the next part is rinse and repeat, right? And now that you know all of the other lengths, you can pick whichever one you want to use to find f sub u. So I'm going to do it this way. I'm going to actually flip my ratio. Come on. Sine of 30 is equal to f sub u over the sine of 120 degrees, right? Remember, it's always across, always across. Okay. This makes it easier to solve for f sub u because you should have 600 times the sine of 120 divided by the sine of 30. Sine of 30 is 1/2 always, right? So that's dividing by a half. You're actually going to be multiplying it by 2. When you crunch this, you're going to end up with, if I write it down there, you guys will be able to see it. Guess we'll find out. I'm going to bring this up here. You guys can see it. £1,039.23 is the magnitude. And obviously you already have the angle. It's at 30 degrees off of the horizontal, right? So we know everything we need to know about that vector. The interesting thing about this is that it is larger than the resultant, right? Which is fine because that 600 is a magnitude and it's actually going to be negative, right? Because it's down and to the left at 30 degrees, right? Or 120, negative 120. Because this is actually negative 120 degrees. Or you can come all the way around and make it, what, 240? Right? Or you can say it's 30 degrees off of the y, negative 30 degrees off of the y-axis, right? Remember, how we report it is important, right? The negative signs are the difference sometimes between homework answers being correct or incorrect. So sometimes I will say one of the troubleshooting things you can try is change your sign just to see. Sometimes that makes a difference. All right, any questions about this one? We pulled out law of sines, right? Law of cosines is much less frequently used, but does have some application sometimes. That's typically, okay, I know if you're looking for an angle and you have very minimal knowledge about the other angle, like you have one angle and two lengths, law of cosines might be faster. It doesn't really matter one way or the other. But all right, questions, comments, concerns about this? No, no, nothing. All right, quiet today, guys. Quiet. All right, cool. All right. Well, if that's the case, welcome to the exciting world of unit vectors. So we're going to start talking about three-dimensional vectors today, which is super fun. It's but it's a little bit different, right? And this is where bookkeeping is really going to come into play for this, right? So it turns out that in our three-dimensional world, many of our structures exist in 3 dimensions, as is the case. And here we're looking at a power pole that has guy wires helping to keep it upright in high winds. So how are we supposed to give the Cartesian vector form for these, right? And we kind of talked about it. You need to have ijk, right? You have a third direction that you have to report. in Cartesian form. You have to report the X component, the Y component, and the Z component, right? That makes sense. Where it gets tricky is sometimes you're given angles, and sometimes you're not, and sometimes you're given multiple angles, and sometimes using angles makes it really confusing visually, right? Because you're trying to do it in your head, and some people can do it and some people can't, and that's fine, right? Same deal here for this radio tower, right? If you know the forces in the three angles, how do you determine the resultant? What do you guys think? How would I determine the resultant in 3 dimensions? Yes, Tyler, exactly. The same as in 3 dimensions. You find all of your X, Y, and Z components for each of your vectors, you add them all together, and then you're good if you want to keep it in Cartesian. Or if you're asked for magnitude and direction, well, then you got to find the magnitude and the direction, right? You got to find the magnitude of the angle. Magnitude is the same. You just do the square root of the sum of the squares, except you'll have 3 components instead of 2. The angles become a real pain in the angle. Because how many angles do you need to report for 3 dimensions? It's more than one, because it could be existing in all 3 planes, right? And so you typically have what we call direction cosines. So you would report 3 different angles for this if you were going to do it that way. The homework might ask you to do that. I am not going to. In 3 dimensions, reporting in Cartesian is fine, okay? Most people don't think of it that way as angles, right? Okay, right-hand rule, right? So I've got a vector A, and it has a magnitude of A, because we're being super creative with these things. So the unit vector, what is a unit vector, right? Well, the unit vector, it's important to remember that we talked about it a little bit yesterday, I think. The unit vector has a length of 1, right? Has a length of 1. Meaning, well, that's not fair to say. It has a magnitude of 1. I don't want to say it has a length of 1. It has a magnitude of 1. So when you do your sum of the square root, the sum of the squares square root, you'll get 1, right? That's what you'll get. So all of the components will sum to 1 for a magnitude. But the way that we can write it here is that u, we'll call it u. You might see it called lambda in some other notations. This book uses u. And they're using the super awesome notation of bold being a vector and not bold being magnitude. But I like to write it like this. So the vector u sub a is equal to the vector a divided by the magnitude of a. And that gives us a unit vector. Okay, so you can convert any vector that you have into a unit vector by dividing by the magnitude of that vector. Okay, so characteristics of a unit vector, magnitude is 1, has no dimensions, right? Let's check that. Let's say that this is a force vector. This vector has newtons, units of force, newtons or pounds, okay? This magnitude is also newtons or pounds. They cancel, right? No dimensions on a unit vector. And it points in the same direction as the original vector. It just has a length of 1. Think of it this way. You're normalizing a vector to be along the direction of that vector. You know that it has a magnitude of 1, right? So why is that helpful? Well, we'll see why it's helpful in a minute. But we've been using unit vectors, right? I, j, and k are unit vectors, okay? And by being able to use unit vectors in reporting our vectors in Cartesian form, we're multiplying by a vector that has length 1, so we maintain the magnitude of the force, of the position, of the velocity, right? Okay. How do you unit vector? That's a great question. I'm glad that you asked. So we're going to start with this vector. We'll call it A, and A has AXI plus AYJ plus AZ in the K. Great, so it has an X, Y, and a Z component. You can see it drawn out here, right? Here's A, and here are the various components. And that's a super clear picture, so I don't think that there's any issues with looking at that. I'm going to go back for a second. All of these things are going to, whenever we're using a coordinate system for positive and negative, we always use right-hand rule, okay? All coordinate systems will be defined as right-hand rule, and you can see, right, if I point, in this case, in the x direction, I curl my fingers into the y, z is pointing positively upward, right? And so whenever you're drawing a three-dimensional coordinate system, make sure that you're using right-hand rule to determine the sense of the rotation. We'll talk about that a little bit more, right? Okay, so I've got my fancy vector here. All right, then what am I going to do? Well, I know that the definition of a unit vector, which I definitely wrote down in my notebook, because it's really important, and I would definitely recommend writing that down in your notebook for sure, 100%, is u of a, the vector u of a, is equal to the vector a divided by the magnitude of the vector a. Okay, cool. Well, I already have the vector a, so I'm going to have to find the magnitude, right? Well, we talked about it. I find the magnitude by taking the square root of the sum of the squares. It's just like the Pythagorean theorem in this case, but different, because Pythagoras didn't have the vision to look at things in 3 dimensions. He's limited in his scope. Okay, I actually don't know if that's true. He probably invented it. He's a pretty smart guy. All right. Anyway, so then we're going to take this and we're going to divide it by this, right? There it is. So where is it? That one. Oh, okay. I guess not. Cool. Well, anyway, I wanted to give it more light. That was fine. Let's really shine a light on it. All right, anyway, hard to see probably, but there it is, right? And in practice, there we go. All right. In practice, you will have a number here, right? Nobody's expecting you to carry the square root of the sum of the squares through the entire process, right? But in practice, you will have some number. Okay? And in practice, these magnitudes, like ax, ay, and az, should hopefully be known, or we're looking for them, right? Okay. Any questions on how to unit vector, how to create a unit vector? We haven't gone over why you would want to do this, really, but the how is there. Nope, nothing. I'm good. I'm good. All right. So if I want to express a vector in 3D space, in this case, I have a vector f here that you can see is some angle theta y. Call that very creatively because it is directly off of the y-axis. And then some angle phi in the xz plane, okay, off of the x-axis. So in order for me to place a vector in 3 dimensions, I have to give you 2 angles, right? If I want to resolve this into f, so I'm going to resolve it. So what do I need to do? First, I need to do this piecewise. What I can do is I can resolve this into the y component pretty immediately, right? Because this angle is directly off of the y. But that's going to leave me with this vector called fh in the xz plane, right? Because remember what we're trying to do. We are trying to say how much of this goes along the y-axis, how much of it goes along the x, and how much of it goes along the z, right? So in this case, it's pretty easy to get the y component. But it leaves us with an extra vector, f sub h, which is the sine of theta y. Does that make sense? Everyone following me? This is also, this vector, f sub h, sometimes people will call this a projection, right? You are projecting the vector f into the xz plane, okay? Projection is just a fancy way of saying the portion of it that lies in the xz plane, or whatever, wherever you're trying to project it to, okay? Cool. So everyone's good with this, right? So then what do we have to do? Well, you probably guessed it. We haven't done anything with this angle phi yet. So now we break FH into its components, right? We resolve that. And now we have our components, right? And so if you want Fx, It's FH cosine of phi. That should be a phi, right? Which we can break down into, because FH is just F times the sine of theta y. I don't know why there's a cosine there. That should be a sine. Don't write cosine, write sine there, please. Thank you. Sine. These two should be sine. The only one that gets a cosine there is the y direction for theta. I'm going to change that right now. It's bugging me. Oh, never mind. We're not going to change it. It's fine. All right. For those of you playing at home, I will do this. There. Perfect. Sine of theta y. Change it. I'll catch it for next time. It's fine. I told you guys there's going to be mistakes in here. All right. So what's the point? All right. The point is that you need a little bit more information than when we're just working in 2 dimensions, right? If I want to resolve this resultant vector, I need to do a little bit more. And if I'm going to use trig, I need to know a little bit more in terms of the angles that we're trying to use. Okay. Let's keep going. All right. So in this case, lambda is the unit vector. Right? So again, people will interchangeably use lambda or u. You can use whatever. Here's the thing about variables. You can use whatever variable you want to be anything. It's really up to you. But you do need to let me know if you're going to use something weird. Like if you want to call it, I don't know, some weird Greek letter. Let's pick a random one. If you want to call it zeta, cool. Great. Good for you. Just let me know what it is. Otherwise, use u or lambda. Those are pretty common. All right, so the unit vector along the line of action F and cosine theta x, cosine theta y, and cosine theta z are called the direction cosines. So this is what I was talking about before. You can determine the angle off of the x, y, and z axes, and we call those the direction cosines of the angle, okay, or of the vector. So if we have those angles between F and x, y, and z axes, right, we can determine these components directly. So in a nice perfect world, right, you are just given the angle between the vector and each of the 3 axes, and you just find the components directly. Unfortunately, we live in an imperfect world, and more than likely in the real world, it will be very difficult for you to get angles to all of the x, y, and z axes from any instrumentation that you have for force vectors or whatever you're looking at, okay? Not a big deal, right? But we can see how we break this down, right? So if I plug these in for fx, fy, and fz, we get this, okay? And so this is all to say that we have a second thing that our unit vector can be equal to, and those are the direction cosines, okay? So you can use a known unit vector to determine what the angles are, right? Theoretically. And it's kind of a pain, to be honest. But if you already had, I don't know, like this unit vector, let's go back. You had this one up here, the A one, right? Well, then you would just use AX is equal to cosine of theta x, right? And then you can kind of quickly get them. All right. Yep. Okay, so here we go. Here is, I've got some particle in space right here, right? We're going to call that point M. And point M has coordinates x1, x2, and x3. Okay. The direction of this force F that goes from M to N is given by taking the distance between those 2 points, right? And so you would say x2 minus x1, y2 minus y1, z2 minus z1, right? That gives you the distance in all 3 coordinate system, all 3 coordinates between those points. Yes? Tracking? Good. So D is a vector joining M and N, right? I think that you need to understand something here. Multiple vectors can exist in the same space that run parallel to each other. So this force vector and this position vector overlap, right? One is likely shorter than the other if we were to draw it out tip to tail, right? But dxi, dyj, and dzk is the distance that points from M to N, okay? And this force vector, so this blue vector underneath, right? So here's lambda. I really wish they had used different colors for all three, but here we are. Okay. Lambda is the unit vector. It's in the direction of the force. D is this smaller vector that terminates up here. You can see the arrowhead slightly. And F is obviously the force vector. All three of those things sit along the same line of action, right? So why is that important? Because of things like cables and chains, right? If I am pulling something with a rope, what direction is the force traveling? The direction of the rope, right? Okay. I want you to notice that if I have this vector, I can come up with a unit vector for this vector. How do I do it? The same way that we just did it. We take the actual vector and we divide it by the magnitude, right? But we also know that F is equal to the magnitude of the force times the unit vector, right? So if I don't know the force, but I know the unit vector, right? These two unit vectors, whether you're talking about D or F, are the same because it's traveling in that line of action, okay? And that's the key thing that you shouldn't miss here. It's really important, okay? If you have two systems of vectors that are sitting on top of each other and they're in the same direction, the unit vector has to be in the same direction, right? Because the unit vector is just the vector in that direction with a length or a magnitude of 1. That's all that it is. And so I can use position vector to find a unit vector, and then I can use that unit vector to determine force components, right? I don't need necessarily angles. I don't need any other information. As long as I have two vectors, I can co-locate using a unit vector. Does that make sense? You guys tracking with that? It's a big idea that's really useful, right? Because we're talking about systems of vectors now. And so we need to think about, does the directionality of the force help us find the force itself, right? Here we go. This is the same stuff we just said. It's just condensed here, right? The formula for finding the unit vector of any position, right? Again, it's just the same. And you can see, you can write it as the direction cosines as well, right? It's all the same. Again, these are the same. I just wrote them in a different format because, again, I think that the bold, not bold format is confusing. Okay. Questions, comments, concerns on unit vectors right now? We'll get into how to use them in a second. But first, please watch this video.
We've already seen that you can visually represent a vector as an arrow where the length of the arrow is the magnitude of the vector, and the direction of the arrow is the direction of the vector. And if we want to represent this mathematically, we could just think about, well, starting from the tail of the vector, how far away is the head of the vector in the horizontal direction, and how far away is it in the vertical direction? So for example, in the horizontal direction, you would have to go this distance, and then in the vertical direction, you would have to go this distance. Let me do that in a different color. You would have to go this distance right over here. And so let's just say that this distance is 2, and that this distance is 3, we could represent this vector, and let's call this vector v. We could represent vector v as an ordered list or a two-tuple of, so we could say we move 2 in the horizontal direction and 3 in the vertical direction. 3 in the vertical direction. So you could represent it like that. You could represent vector v like this, where it is 2, 3, 2, 3, like that. What I now want to introduce you to, and we could come up with other ways of representing this two-tuple, is another notation. And this really comes out of the idea of what it means to add and scale vectors. And to do that, we're going to define what we call unit vectors. So unit vectors. And if we're in 2 dimensions, we define a unit vector for each of the dimensions we're operating in. If we're in 3 dimensions, we would define a unit vector for each of the 3 dimensions that we're operating in. And so let's do that. So let's define a unit vector I, and the way that we denote that it is a unit vector, is instead of putting an arrow on top, we put this kind of hat on top of it. So the unit vector I, if we wanted to write it in this notation right over here, we would say it only goes 1 unit in the horizontal direction, and it doesn't go at all in the vertical direction. So it would look something like this. It would look something like that. That is the unit vector I. And then we can define another unit vector. Let's call that unit vector, or it's typically called j, which would go only in the vertical direction and not in the horizontal direction. And it goes 1 unit in the vertical direction. So this went 1 unit in the horizontal. Now j is going to go 1 unit. J is going to go 1 unit in the vertical. So j, just like that. Now, any vector, any 2-dimensional vector, we can now represent as a sum of scaled up versions of I and j. And you say, well, how do we do that? Well, you could imagine vector v right here is the sum of a vector that moves purely in the horizontal direction that has length 2 and a vector that moves purely in the vertical direction that has length 3. So we could say that vector v, let me do that same blue color, vector v is equal to, so if we want a vector that has length 2 and it moves purely in the horizontal direction, well, we could just scale up the unit vector I. We could just multiply 2 times I. So let's do that. Is equal to 2 times our unit vector I. So 2I is going to be this whole thing right over here, or this whole vector. Let me do it in this yellow color. This vector right over here, you could view as 2I. And then to that, we're going to add 3 times j. So plus 3 times j. 3 times j. Let me write it like this. Let me get the color. 3 times j. Once again, 3 times j is going to be this vector right over here. And if you add this yellow vector, right over here to the magenta vector, you're going to get, notice we're putting the tail of the magenta vector at the head of the yellow vector. And if you start at the tail of the yellow vector and you go all the way to the head of the magenta vector, you have now constructed vector v. So vector v, you could represent it as a column vector like this, 2, 3. You could represent it as 2, 3, or you could represent it as 2 times I with this little hat over it, plus 3 times j with this little hat over it. I is the unit vector in the horizontal direction, in the positive horizontal direction. If you want to go the other way, you would multiply it by a negative. And j is the unit vector in the vertical direction. As we'll see in future videos, once you go to 3 dimensions, you'll introduce a k. But it's very natural to translate between these two things. Notice 2, 3, 2, 3. And so with that, let's actually do some vector operations using this notation. So let's say that I define another vector. Let's say it's vector b. And vector b is equal to, I'll just come up with some numbers here. Vector b is equal to -1 times I, times the unit vector I, plus 4 times the unit vector in the horizontal direction. So given these two vector definitions, what would be the vector v plus b be equal to? I encourage you to pause the video and think about it. Well, once again, we just literally have to add corresponding components. We could say, okay, well, let's think about what we're doing in the horizontal direction. We're going 2 in the horizontal direction here. Now we're going -1. So our horizontal component is going to be 2 plus -1. 2 plus -1 in the horizontal direction. And we're going to multiply that times the unit vector I. And this, once again, just goes back to adding the corresponding components of the vector. And then we're going to have +4, or +3 plus 4. Let me write it that way. +3 plus 4, 3 plus 4 times the unit vector j in the vertical direction. And so that's going to give us 2, I'll do this all in this one color. 2 plus -1 is 1i. And we could literally write that just as I. Actually, let's do that. Let's just write that as I. But we got that from 2 plus -1 is 1. 1 times the vector is just going to be that vector. Plus 3 plus 4 is 7. 7j. And to see this is exactly how we saw vector addition in the past, is that we could also represent vector b like this. We could represent it like this. -1, -1, 4, -1, 4. And so if you were to add v to b, you add the corresponding terms. So this should be equal to, if we were to add corresponding terms looking at them as column vectors, that is going to be equal to 2 plus -1, which is 1. 3 plus 4 is 7. So this is the exact same representation as this. This is using unit vector notation, and this is representing it as a column vector.
Yep. Fantastic. Earth-shattering, if you will. Okay. Okay, we've got this 3-dimensional problem now. It's gross. It's gross. Okay. So I've got 2 forces, F1 and F2, that are applied to a hook. You can see the hook very clearly drawn right there. And the resultant force we want the resultant force in Cartesian form. So we're not looking for angles of any sort. We are just looking for the Cartesian. We want the I, J, and K components written out. Here we have a plan, right? So the plan that we're going to use is we're going to use geometry and trigonometry to write F1 and F2 in Cartesian vector form. And then we're going to add the 2 of them together to find the resultant, right? It's pretty straightforward. Okay. What's kind of gross about it is that we've got a couple of different odd things, not odd things, but things we haven't seen before that we need to deal with, right? So let's start with F1. Okay. So we're going to start by resolving the force F1 into its components. The thing that's weird about this, and you can see the diagram up in the right-hand corner, right? The thing that's weird about it is the way that it's drawn, you can't really tell what this is trying to tell you, I don't think. I don't think it's super clear. But this is trying to show you that this force exists only in the YZ plane. So this is a 2-dimensional force vector. Is everybody seeing that? I know it's weird, right? So if we were to redraw it, let's just look at the YZ plane, okay? Let's just look at the YZ plane. So we'll do this guy. I'm going to redraw my YZ plane with very flat straight lines. And then we're going to take our vector and we're going to say, here's our vector F1. That's equal to 500 pounds. And we know that this is a 3, 4, 5 triangle, right? So based on this, it's pretty clear that we can get the X and Y components for F1, right? So Let's go ahead and do that, right? So F1 in the X should be what? Well, it should be F1 times, we already did this one earlier, right? The book likes to, so you'll notice something about the textbook. Textbook tends to use 3, 4, 5 triangles and 30-degree angles quite a bit, right? Because they're easy. They're easy to write problems for and they're expected. Don't get used to it in the real world. Things aren't super neat and tidy, but it certainly makes this a lot easier. All right, so if I want the X component, what is it in this case? That's correct. 0 in the I. What about the Y component? How do I get the Y component? 4/5 times, we'll just call it F1 for completeness rather than 4/5 times 500. So this is an easy one. That should be 400 pounds. Yeah. Quick maths. Does everybody see why we're using 4/5? We get why we're using 4/5. We went over it before, right? We need the cosine of that angle, right? We know it's 4/5. Yeah.
You guys.
I did. Good catch. Thank you. I certainly did. I was wondering when you guys would notice that. Jeez. Right? That's F1. Yeah. Double. Double strike. That's 2. We're early. We have to end class soon. All right, maybe I'll get this one right. In the Z direction, what do we got? 3/5 of F1, which is 3/5 of 500, which should be 300 pounds. Fantastic. So we can rewrite F1. We'll do it up here for now. It's going to be 0 in the I plus 400 in the J plus 300 in the K pounds. Right? Now, some people will tell you that you don't need to carry this 0 here. And those people, that's fine for them. But it eliminates us having any issues if we write everything as IJK. Okay? Why? Because potentially there's a vector that has 0 in the J or 0 in the K. And then you're not lined up with the other ones and you forget and you make a mistake by adding a K to a J or something like that. So I would recommend bookkeeping the entire vector. Okay? That's what I would recommend. Now you're all adults and you can do what you want, but there we go. Okay. All right, so that's F1, right? Oh, that's F1. Any questions on how we got F1? We good with that? Everybody good? Yeah. All right, because now we're going to do F2. I'll get rid of that. All right, so here's F2. Okay, and F2, they give us an angle from the x-axis, right? And an angle from, where is that from? So hard to see. From the XY plane down to F2, right? And you can see the book here has drawn these two components for us. And that kind of makes it confusing, I think. But here, let me. So, all right, what are we going to do first? First thing I'm going to do is I'm going to show you what this looks like in the XZ plane. Okay. Why? Because if you were to turn this 90 degrees so that you're just looking at the XZ plane, we just have one vector there, right? And that is this vector. And what is that vector? That is vector, no, not vanishing pen, that would be horrible. This is F2, right? And that's equal to 800. Great. Why did I want to draw it that way? Because if we go back up, right, and I'm going to leave my drawing there for a second, but we're going to go back to the original drawing here. If you go up here, right, the only vector that we're given, we weren't given those other two to start with, right? We just have the result. We're going to break it down. But by looking at this, right, we need to do a couple of steps, right? The first thing is we need to figure what part of this is in the Z, and then project the rest up to the XY plane, and then figure out what our X and our Y is, right? So remember that the thing we went through earlier, right? Where we had a couple of different, here, go back. So if you look at this, right, they have F2Z and F2 prime, right? But we're going to start off just looking in the XZ plane, and if I do that, this is given as 45 degrees, right? And so I can find the X and the Z components, right? Well, not really the X. I can find the XY plane component, right? Because that doesn't sit along the X. It looks like it would be when I look at it in 2 dimensions, but when you look at it at 3, it's at an angle, right? So what we're going to do first is we're just going to find F2Z, right? So F2 in the Z direction is got to be what? If I want the Z direction component of F2, how do I find it? All right, say that one more time. Okay. Sure, right? Negative times the magnitude of F2 times the sine of that angle that it's at. It's 45, which is negative. No, no, no. No, no, no. There we go. Which is negative 800 sine of 45 degrees, which we would calculate as roughly negative 565.7 pounds. Right? And that's F2 in the Z. What we are left with is the XY component, right? This F2 prime here. I'm going to call it F2 prime because that's what the book is calling it. You can call it whatever you want. The other example we use, they called it F sub H, right? It doesn't really matter what you call it, but it is its own vector, right? And that's the rest of it, right? And so that's going to be what? Well, that's going to be F2 cosine of 45 degrees, right? Because it's very clear that that looks like to me that it's going to be in the positive X. Like if I was to bring that up, that would be at least positive in the X. I can't make any determination really about the sign, but it looks like it would be positive to me at this point. So we're going to leave it, right? And we can calculate this, right? Because it should just be, since it's 45 degrees, it should just be 565.7 pounds. Yeah, everybody tracking with me on that? Yeah, Colin. So it's this guy up here. So what's that? Yes, that is the projection onto the XY axis. So good question. So remember what we're trying to do, right? This thing exists in 3 dimensions, and we need X, Y, and Z components. If we're looking at this, how do you know that you want to go after the Z component first? Well, it's the only one that we can get with the least amount of trig, right? If you look at that. Again, in an ideal world, if you have angles to each of the axes, you just do it directly. But we don't. We only have 2 angles, one of them goes from the x-axis and one of them comes from the plane, right? You can see that it's coming from the xy plane downward, okay? So when I look at problems like this, I try to think about what can I get right away and then what's left over, right? Pretty much, so right away, I know I can get the z component of this, and what's left over is whatever is in the xy plane, right? And so now if you were to turn this and look down at the xy plane, right? So do that, which actually, when you draw it, looks like this, right? Because of the way that things are. And remember, if you're ever concerned, right? Positive x in the y gives me positive z out of the board, which tracks with this coordinate system, right? You can always check it. Z in the x gives us y coming out. Okay, so now we have this vector, which we have called f2 prime, and we know that that angle is 30 degrees. Yeah? And so this is just a quick trig decomposition for this, right? And so if we want f2 in the x, it's actually f2 prime times cosine of 30 degrees, and f2y is f, not 5, but f2 prime sine of 30 degrees. And based off of this, both of these should be positive, right? Because they're pointed to the left and downward, which is how positive is defined for this. Yeah. Is everybody tracking with me on this right now? We good? Questions, questions, questions. Any questions? No? Okay. So if you were to write this out without solving for f2 prime first, right, you would have f2 times the sine of 45, or f2 times the cosine of 45 degrees times the cosine of 30 degrees. So you're taking the cosine twice, right? Taking the cosine twice. So let's finish it up. Let's get the x. We have the z component. Let's get the x and the y components. So if we crunch these numbers, right, we have our 565.7 times the cosine of 30 degrees. We get 489.9 pounds. And in the y direction, we get something similar, except we're using the sine of 30 degrees. The nice thing about the sine of 30 degrees is we know that that's 1/2, so we should just be cutting this in half. And so we end up with 282.8 pounds. Okay. So we can write F2, right? So I'm gonna get rid of this for a moment. We'll write down F2. Does anybody still need that? Are you done writing that? Yeah. It's gone forever now. Just kidding, it's back. Oh, all right. So rude, jeez. All right, F2. Let's put that up here. In the X direction, what do we have? Well, we had 489.9 in the I plus 282.8 in the J, and then the K direction is actually negative, right? Minus 565.7 in the K, and that's in pounds. Okay. So that's great, but we were asked to find the resultant, right? Asked to find the resultant. So what do? Well, we just add these things. And if you wrote these out as IJK, this is pretty easy for us to add together because you just write your I, your J, and your K together, right? So we could be like, we could do that, right? And this should be 489.9 in the I plus 682.8 in the J and minus 266 in the K pounds, right? And we'll clean this up so that it actually is done, well, it's fine. We'll leave it like that for now. It's fine. And there it is. It's the whole thing. So more complicated in the sense that we have this nasty trig, and I think nasty is very relative. If this is the worst trig that you have to do, it's really not that bad, right? But we have to think about this when we have 3 dimensions. The takeaway is it's all right. So what is the takeaway, right? That's a good question. When you have stuff in 3 dimensions, sometimes it's not intuitive. Okay, full stop. That is going to become very evident when we start talking about moments in 3 dimensions, right? Rotations in 3 dimensions. When things are rotating, it's not intuitive. It's just not. However, right, if you do this in vector form and you trust your bookkeeping and your math, you can get through this, okay? The keys here are think through the problem, right? And I will be very honest with you, working with angles in 3 dimensions is tricky, right? Because if it's not drawn well, it's really hard to see what they're trying to tell you, right? So really take the time to set up the problem because the mathematics on the back end is not the biggest challenge here. The front end is the biggest challenge, the setup, right? Getting stuff set up the way that it needs to be so that you can execute the math is what we need to focus on, okay? Because you guys can add these numbers together. That's really easy, right? But visualizing it sometimes is hard. So I would say if you can draw it in 2D, right? See if you can visualize it in 2 dimensions. See if there's any easy relationships that you can come up with, right? I mean, when I did this problem, I had 5 different drawings in different directions for it, right? You can use software tools to help you with this, right? MATLAB will plot vectors for you, and you can just, in a 3-dimensional plot, move it around so you can visualize it. There's no rules against doing that to help you learn it and understand what you're doing from a mathematical standpoint, right? If you're doing your homework, I would encourage that. We're probably not going to have MATLAB on exams or quizzes. Sorry, they're not exams. I don't want to freak anyone out. No. Yeah. Anyway, questions, comments, anything? Anybody? You guys feeling okay with that for right now? Yeah. I mean, let Desha, I see that as a good question. Are you ever going to be asked to find the magnitude and the angles? Potentially, and we'll talk about that in a second. I have an example for that. We'll go through that. Appreciate the setup. I mean, I think you can tell that there might be certain applications where an angle might make sense, right? Angles might make sense. But there's also certain applications where, maybe we don't care what the angle is. We just want to know this is how much force I have in the X direction. All right. So 6 of 1 really just depends on what we're trying to do. All right. Position vectors and force vectors. Where are we at? Perfect. All right, so what do we want to be able to do? We want to be able to represent a position vector in Cartesian coordinate form from a given geometry, and we want to represent a force vector directed along a line of action. Okay, this is what we were talking about, right? We have guy wires here, and so want to know how much force is being transmitted through that wire, right? The way that wires work, where the cables work, they should all be in tension. You should never, somebody comes to you and says, I have this great idea for a design where I'm going to use these cables in compression. You should politely decline whatever they're offering you because you cannot. I mean, if you ever tried to push on a piece of cooked spaghetti, that's essentially what you're trying to do. You can't really transmit force through that. Okay. Anyway, long story to say, we transmit force through a cable in the direction of the cable, right? So you can't have a force that is directed like, okay, I have these two things tied here, so my force is coming perpendicular to this cable. That's not really how cables work. Now, can you? Yeah, sure, if I push on it, fine, whatever. But if I just have the cable there and I'm not acting on it from an outside force, it's just pulling down. It's there to tether whatever I am holding up, right? Okay, so the position vector RPQ is obtained by doing what? So if I have 2 points, P and Q, and I want you to give me the position vector from P to Q, how do I do that? Do I take the coordinates of P minus the coordinates of the origin? Do I take the coordinates of P minus the coordinates of Q? Do I take the coordinates of Q minus the coordinates of P? Or do I take the coordinates of the origin minus the coordinates of P? What do you guys think? Is it A, B, C, or D? Let's start we'll start with A. Who thinks that it's A? No takers on it? All right. Who thinks that it's B? P minus Q. Okay. Who thinks that it's C? Q minus P. All right. And who think it's D? Origin minus P. Who doesn't want to answer because you're afraid to be wrong and don't want to look like you just don't understand? Thanks, Caleb. Appreciate the honesty. You can also do this, by the way, you can also do this by taking the coordinates of Q minus the origin and then the coordinates of the origin minus P and then putting those together. But that's the same as doing the coordinates of Q minus the coordinates of P. So remember, it's a distance thing. Is this technically wrong? No, you'll get the same distance. It's just pointed in the opposite direction, right? The thing about distance is that it should be the same between the 2 points, whether you use one set minus the other or the opposite. It's just going to change your direction. Big thing about how we report vectors is the standard format is to say PQ means go from P to Q, right? We can talk about relative positions, but that's not really anything that you need to worry about for this class. All right, here's another one. P and Q are 2 points in 3D space. How are the position vectors RPQ and RQP related? We just kind of talked about this, but oh, yeah. Just shout it out. I was as loud as you can. B. D. D. What are you guys saying? No, all right, I got you. B. All right. It's B, right? We just talked about this. If you're going to flip the direction, you have to flip this sign, right? Okay. Now I will say this is not telling you that this is necessarily directed in the positive direction, right? RPQ could be negative, but then you would have to take the negative of that for the other way and would make it positive, right? Okay, great. All right, a ship's mooring line connected to the bow can be represented as a Cartesian vector. Why? Because everything can be represented as a Cartesian vector. And so what are the forces in the mooring line and how do we find their direction? That's a good question. You would probably have to have more information than what I give you on this screen, right? And why would you even want to know that? Maybe I don't like boats. I don't want to go on a boat. It's fine, right? Well, I mean, I guess whoever owns that boat would want to know that, right? Because if this mooring can't take that force, then you're going to have a bad day. It's going to rip out of the ground. So also similarly, if your cable or whatever rope you're using isn't rated for that strength, you're also going to have a bad day, right? So you need to know, somebody needs to know what that force is. Maybe not necessarily you, but somebody, right? It's important for somebody to have investigated that at some point. Okay. What about this? Awning. The awning is held up by 3 chains, right? What are the forces in the chains and how do we find their direction? well, again, what would you need? What would you need if I asked you to find the force here? What would you need? If I asked you to find the force, what would you need? Okay, sure, right? Probably need to know something about the awning, right? What other things? Like if I know, what do I have to know about these chains to find the force in the chains? Like angles, sure, sure. Yeah, you need to know the weight of the awning for sure. So angles or what? Maybe the positions, the distance vectors, right? We talked about that a little bit. If you can find a unit vector for that distance and you know that the force vector also goes along the chain, then you can find forces given that you have some information, right? So position vector is defined as a fixed vector that locates a point in space relative to another point. So we talked about this earlier, right? So if I have A and B and I want the vector between there, right? The big takeaway is whenever you have any points in space and you're looking for distance, remember that a vector specifically is a set of directions to get from point A to point B, right? So like if you were to look at a map of GCU from the top down, right, and say, I wanted you to give me specific directions to Panda Express, right, from building 1. Well, if we set up our XY coordinates to be Y being positive north on campus and X being positive to the east on campus, so that way, right? How would I do it? Well, I would need to travel some distance north, right? And I would need to travel some distance east, right? And I would probably report those in a vector as X and Y. And it doesn't really matter if, well, I mean, if there were nothing blocking my path, it wouldn't really matter if I did the X part first or the Y part first. I would still get to the same location, right? Because the vector is there. Right? And that's what's important, right? Here is when we have a vector, right? If we're a vector A to B, that is the distance from A to B. BA, right? And so that really remember that notation, right? Because it's going to be super helpful. Right. All right. RAB, we already talked about this, right? If you want the distance, you need to subtract one from the other. And that is basic math for determining the distance between 2 points. Okay, great. Force is directed along a line, then we can represent the force vector in Cartesian coordinates by using the unit vector and the force's magnitude. We talked about that. The force vector F is equal to the magnitude of the force times the unit vector. This guy right here, right? Remember, the book uses this weird thing, right? But what unit vector, right? Well, if I want the force from A to B, I need to find the unit vector from A to B, which is the distance from A to B divided by the magnitude of the distance from A to B. Then I can put this in here, and if I know the magnitude of the force, or I can find the magnitude of the force, I can find the full unit vector, or the full vector for the force, right? So find the position, find the unit vector, use the unit vector to find the force, right? Okay, let's talk about it with this problem. So I got this guy wire. I was told that the tension in this wire is 2,500 Newton, right? I have to do 2 things. I want to find the components Fx, Fy, and Fz of the force acting on the bolt at A. And I need to find the angles to the X, Y, and Z axis for this force, right? So again, the tee up was perfect. Thank you. All right, so one of these things, hopefully you're like, that doesn't seem too bad. And one of these things, you're probably like, I really don't want to do that because I don't feel like finding angles of things, right? I'm guessing based on personal experience, but also from what I know about just teaching this class in general. Okay, so what do we have to do? Well, let's start off this way. We're going to do this. First thing I'm going to do is I'm going to draw my coordinate system. So based on the previous picture, I should have something that looks somewhat like that. Right. All right, I'm gonna X, Y, Z. Let's check it. X in the Y, positive Z. Right-hand rule has been appeased. Perfect. Okay. Point A. Let's define point A before we start drawing things. Point A. I don't know. I'm going to say that point A is somewhere over here. Okay. I'll label it with an A. Okay. Um, Point B, we'll say, is somewhere up here. Why am I going to bother drawing point B? I want to make sure my vector is pointing in the right direction. It has to go from A to B, right? Again, not drawn to scale, so anybody who is, at me in the comments, I guess. There we go. And then we'll call that FAB because we're very creative with our naming conventions. And that was 2,500 Newton. Okay. And we're given some, if you go back to the original, right, we are also given some distances, right? And so we're told that this here, from here to here, is 30 meters. From the y-axis over is 40 meters, not whatever that was. Okay, and then the last one is we're given the distance from the ground all the way up to B, which was 80 meters. Okay. So we were asked to find Fx, Fy, and Fz for FAB, right? Some people might call it FABX, FABY, and FABZ, which would probably be a good idea, right? But we only have the one force, so in this case, it's not super bad. But in practice, it's definitely better to use the subscripts, right? So AB, AB, AB. All right. So I don't have any angles. Bummer. Not really, though. What am I going to do? Well, Dr. D just went on this big tirade about how we need to use unit vectors to do something with positions and blah, blah, blah. Yep, we're going to do that. So I'll draw this parallel because it'll block out the other one. What's this thing that I've just drawn? Yep, the distance vector. And I'm going to very creatively, call this R, AB. Because again, I'm super good at naming things. And people keep letting me do it. I named a couple kids, this is great. Really found I'll probably come up with nicknames for most of you guys. That's by the end of the 7 weeks. It's gonna be awesome. Okay, so I want RAB. Let's find RAB. And first, let's get rid of this guy. No bogeys on the screen today. All right, so first thing we're gonna do, since we want these forces, right? What do we know? Well, we know that the force vector AB has to be equal to the magnitude of our force vector AB times the unit vector AB, right? And if you don't remember that, definitely write that one down because that's going to be an important one. Where does that even come from? Okay. Remember that the unit vector AB is equal to the vector divided by the magnitude of the, right? So we just rearranged that. But it's also equal to the vector of the position over the magnitude of the position. So that's where we're going right now. We're going to find UAB first. So let's do that. If I want to find UAB, I need RAB divided by the magnitude of RAB. Okay. Would anybody like to take a guess, hazard a guess, at the vector that gets me from A to B? That is the position vector. You said minus 40I minus 30J plus 80K. That's a meter. Well, let's see. Let's do the walk. This work? Yeah, hey, look at that. Okay, so yeah, I would have to go negative 40 in the x direction. Oh, that was not helpful. There we go. I have to go negative 40 in the x, right? Then I'd have to come down 30 in the j, and then I have to go up 80 in the k. Yep, there we go. Cool. All right, so we've got half of what we need for that unit vector. Now we just need the magnitude of RAB, which I have not gone through the formality of keeping the negative sign in there, as it turns out that negative 40 squared is the same as 40 squared. I am positive on that one. Well, feel free to post in Discord, not Discord. Feel free to post in Halo. I'll make a discussion question, and David can write the proof for negative times negative being positive. I think that seems fair for everybody. Okay. Is everybody okay with that? Did we see where that comes from? Yeah? All right. So if we add all of those together, square them, and take the square root, we get somewhere around 94.3 meters. All right, so that's the magnitude of that vector. Okay. So the unit vector itself is negative 40 divided by 94.3 in the I, minus 30 divided by 94.3 in the J, plus 80 divided by 94.3 in the K. And that's unitless, right? Because meters divided by meters gives me units of one, units of unity. I'm going to leave it like that. You can feel free to crunch those numbers if you want. Is everybody okay with how I wrote that? You can take the full vector and just divide the whole thing by 94.3. But if we want to find I, J, and K components for something, we probably want to be able to scale it in the I, J, and K, right? And so remember that the 94.3 is a scalar because it is a magnitude. and regular algebra rules apply, right? I can dividing the whole thing by a number is the same as dividing each component by the number, right? Yeah, good. Well, it's not the answer yet. So at this point, you can do it however you like. I like to keep it this way, mainly because there's other problems where the numbers work out nicer and you'll end up with like 2/7 or 3/7, right? And like that's not a bad fraction to keep around. These are not great, but I would rather have it fractional than keep. So I think if you're looking for accuracy's sake, I would recommend keeping it fractional until the end when you do your truncation for decimals, because otherwise you're going to have some rounding issues, and then you might end up having stuff that the textbook considers wrong in the homework because you rounded during the process instead of at the end, right? So keep as many. Fractional is going to be more accurate for longer, essentially. And that, but you're like, well, that's not actually 94.3, Dr. G, so you already messed it up. Yeah, it's true. It's fine. I think we're gonna be okay. I don't know. Let's have this feeling. Have this feeling. Guys are all right. Not for this. This is when you're looking for the unit vector, you kind of need the numbers to be able to do it. I will, just for completeness, since I have it here, right? So it's negative 0.42 minus 0.32J. Okay. Okay. So far, so good, right? Doing all right. All I did was I simplified it, even after the whole thing where I said I don't want to simplify it, but there we go. Based on what we have up here, we want to find the force. We know the magnitude of the force, right? We were told that we have 2,500 Newton in that guy wire. So we already have that. So really, you don't have to put that in the absolute value, but here we are. Now I have the unit vector, right? So let's sub in our unit vector. Another way to think about a unit vector is it's basically telling you what percentage of the total magnitude goes where, right? Kind of. Because then if I say that, you're gonna be like, well, 42 plus 32 plus 85 is way more than 100, Dr. D. So, you know, you're right. It's math. It's just how math. You got to remember that magnitude is not calculated by just adding it, right? If you want to test it, right, if you did the magnitude of UAB, so 0.42 squared plus 0.32 squared plus 0.85 squared square root should come out to 1. You can always check to make sure your unit vector is acting appropriately, right? But then we multiply through, right? And so what we end up with is negative 1050I minus 800J plus 2125K. And that's Newton. And there we have it, FAB. Right. Second part of this is to find the direction cosines, which we talked about is going to be the angle from the X, Y, and Z axes directly to our force vector, right? But we'll do that in a second. Any questions on this? If you see a problem, yeah, Raph, what's up? That's Newton. This is the units. Oh, that's meters. Yeah, you want to have the units. Yeah. So that's a distance vector, right? Up there. Yeah. Yes. It's 94.3 meters is the magnitude, right? It still has units because when you divide them, the units cancel. That's why it's a unit vector with no units. Because if you don't provide that, then it's still in meters, and then we end up with Newton meters, which is not a unit of force. It is the unit of torque. Okay. Um, yeah, any other questions on this? No? Okay. So we want to find the direction cosines. That was part B. How do we go about doing that? It's actually not too bad given everything that we have right now. So I'm going to erase some of this so that I have some more room to work, right? Just going to just keep that. Yeah, what's up? Mm-hmm. Mhm. Okay. For the homework, I'm not sure. For me, it's close. I would, so here's the thing. I will go through, I will painstakingly go through and look at all of your work. So again, I'm gonna just remind you guys that I know because the homeworks are online, you don't necessarily feel compelled to have a ton of scrap work to do them. But on quizzes, magic answers don't get points. Okay. I need to see your work because I am less concerned with you being able to get the right answer and more concerned with your process for solving problems. I'm trying to get in your head. I want to see if you are thinking about the problems correctly. And so over communicate with me through the amount of work that you put on the page. Okay. I've had students in the past who put down I stowed this variable as X in my calculator, and then I'm like, it's not like I don't need calculator commands for you to write. I just need to see the actual work, right? I need to see the work. Okay. Um, Next thing, we want to find theta x, theta y, and theta z. Okay, so there was an equation a few slides ago that we've all definitely forgotten, but we should have written down that told us something like, well, if I have a unit vector that's equal to the cosine of theta x in the I plus the cosine of theta y in the j plus the cosine of theta z in the k. And if you didn't write that down, this is a great opportunity for you to put this in your notebook, right? As the what's the new guy from Blue's Clues? Josh from Blue's Clues would tell you. Steve is missing. Actually, that's not true. Steve lives in New York and is a private detective in New York, according to the Blue's Clues movie, which is canon. And this video is probably going to get flagged for copyright because I mentioned Blue's Clues. Thanks, Nickelodeon. Way to go. You bring lawyers into this. All right. Anyway, we've got that, right? And so I erased it, but I'll rewrite it here just so that we have it. We also know that UAB is equal to negative 0.42 I minus 0.32J plus 0.85K. Well, that's fantastic news. And you're like, no, it's not. That's gross. No, it really is fantastic news, right? Because what do I have here? I have two vectors that have to be equal because they're the same vector. Okay? So what can I do? Well, I can just say that negative 0.42 has to equal the cosine of theta x. So the cosine inverse of negative 0.42 is equal to theta x, which is equal to, somebody hit me with it. $115.1 degrees. We're going to do the same thing. All right, what's theta y? And finally, theta z. There we are. We have found the angles from the x, y, and z axis. So if you were to look at our drawing, which I will pull up, maybe there, right there, and I'm going to clear the math for a second so we can actually look at it. Don't worry, I'll get them back. What this is saying, right, is the angle from the x-axis, that's theta x, that's theta y, and that's theta z. I know theta y just looks like a straight line. It's hard to draw. It's because you're not looking at it from the appropriate perspective. If you were to rotate around it, you would see it's very curved from the other side. Anyway, okay. Does that make sense? Probably not, but that's what happens. All right. There we go. So anyway, that is the mystery of the direction cosines, right? Like questions about that. Why is that useful? There are some problems where you're just like, it's a gift. It feels like a gift from God when you open up to a problem and there's just, here's the angle directly from all of the axes and this is find me the components. It's really nice because it makes it a lot simpler, right? But that's not necessarily the case a lot of the time. Yeah. Okay. What is phasers? Phasers. So if you want to deal with vectors in the imaginary plane, then, and you do, because based on the fact that you're an electrical engineer, that's what you signed up for. Laplace transforms, all that good stuff. Fast Fourier transforms. Hey, if you guys want to look forward, and this goes for everybody in the room, if you want to look forward to one topic that is coming up, I will tell you, it's got to be, and it's not in this class, but Laplace transforms, okay? Laplace transforms, if you don't like differential equations, but you like algebra, you're going to love Laplace transforms. No, man, best. All right, let's talk about dot products, right? So what more vector operations, right? So if you know the physical locations of 4 cable ends, how can you calculate the angle between the cables and the anchor, right? So is there a way that we can back calculate, given that I have say I just have 2 vectors, right? I have 2 force vectors, and I know exactly what they are. I don't have any other information. Can I back calculate the angle? Sure you can, right? And that's helpful, right? For the force vector F applied to a wrench at point A, what component of it actually helps turn the bolt, right? Is there a way that we can quickly determine how much of that force actually goes into turning the bolt? All right, sure there is. Okay. A dot product, also sometimes called a scalar product. Why is it called a scalar product? Because when you do it, you're going to get a scalar. You will not get a vector from a dot product. You will get a scalar. A dot product of two vectors is defined as A dot B, which is equal to the magnitude of A times the magnitude of B times the cosine of theta. And so now you can see that if you have both of these vectors and you take the dot product, right, you can use that dot product to determine the angle between them, right? Okay, angle theta is smallest angle between two vectors and is always in the range of 0 to 1. Right? What are the characteristics? The result is always a scalar. Talked about that. And the units of the dot product will be the product of the units of A and B. So it'll be Newton square, right? It'll be meters square, right? If there's two vectors, if there's more than two vectors, you're taking the dot product of Newton's cubed is a great unit. It's fantastic. All right. Scalar product or the dot product between two vectors P and Q is defined as such. So here's P and Q. I want the angle. I use the dot product. We already went over that. But here's the thing. Dot products have some algebraic rules that are allowed and some things that don't compute, right? So you can use the commutative property. You can say that P dot Q is equal to Q dot P. That's totally fine. They are distributive. So if I have P plus the resultant of Q1 and Q2, I can say, well, that's the same as the dot product of P and Q1 plus the dot product of P and Q2. Also fantastic. But they're not associative, right? So I can't say that P dot Q dot S is equal to P dot Q dot S, right? I can't move the parentheses over here. The order matters, right? The order matters. Great. Scalar products with Cartesian unit components. Okay, this is a big deal. So, well, it's a big deal. You don't have to memorize this, and you think that you might have to, but you don't. Okay, so if I have two unit vectors, I dot I, and I take the dot product of them, it comes out to 1. Why? Well, what's the angle between I and I? 0. What's the cosine of 0? 1. If I have two vectors that are 90 degrees apart, like I and j, if I take the dot product of those two, it's 0. Why? What's the cosine of 90 degrees? 0. That's why. And so what you'll notice is that if you take the dot product of things that are parallel to each other, that will work. But if you take the dot product of things that are orthogonal to one another or offset by 90 degrees, you will get 0. And so you can eliminate them, right? And so when we take P dot Q, where that's x pxi plus pyj plus pzk and qxi plus qyj plus qzk, all of the orthogonal pairings go away. So you end up with, well, you have to multiply through all of them, right? So px times qx and the I, well, I and I is a 1, so that stays. But I and j and I and k, well, ij, ik, those are 0. Those go away. Same deal for the other ones. So we're just left with pq times px times qx plus py times qy plus pz times qz. Okay? So it simplifies things a lot. And if you wanted to take the dot product of something with itself, you end up with just p squared. Great. Great and good. This is important, right? This is a nice thing to know, right? It helps simplify a lot of things. And it's different when we're going to talk about cross products. Because we'll talk about cross products on Thursday, not tomorrow. Tomorrow is a day of rest like the good Lord intended, right? No, do on Thursday. Yeah. It's due for you. All right. Okay, any questions about this, right? We still haven't really talked about why this is useful in any way, right? Like, yeah, we can get the angle between two things, but is that really something that we need? It depends. Depends on what your application is, right? You might need it. Oh, might not. I don't know. I don't know what you're doing. Um, Here's another thing that we can look at, right? So angle between two vectors, okay? So check this out. If you were to take P dot Q, right, that's P times Q times the cosine of theta, right? And so we talked about P times Q over here, right? And we already got it. So we plug that in. That is weird because that kind of looks like a unit vector, doesn't it? Because it is a unit vector. Because remember the direction cosines. Because we just did that. Okay. It's the scalar part of it. We can also use this to get the projection of a vector, right? And so we talked a little bit about this earlier, right? And you might recognize that from that problem where we had that force that we had to project up to the XY plane, we kind of did a dot product without really saying we were going to do a dot product, right? And so if you have a force, you can project it along any line that you want, right? Or two forces, you can project them, right? So if I have POL, right? So the force from O to L, that's P times the cosine theta, and that's the projection of P along L. So you can see this line drops down, and we have this much projected onto. So think of it this way. If I was holding a baseball bat, let's hold this thing. I'm holding this thing, okay? Came in handy. I'm holding this thing. What's the projection? Well, if it's at an angle, it's literally the projection of this on the screen. It is the shadow. How much of a shadow is P casting on the line OL? That's what the dot product lets us see. What component, how much of this force is applied in that direction? Okay. And so if you have a force that you want to know along a direction that's not necessarily orthogonal to it, not X, Y, or Z, you can use dot product to find it, which is actually super useful, right? And you can see how that kind of comes out. As long as you have the cosine of that angle, you can get that. Great. All right, and if you have an axis defined by a unit vector, guess what? It turns into your standard direction cosines that we already talked about. So I know everybody loves derivations of equations. It's probably everybody's favorite. You know, we're just don't. I try to keep them to a minimum. I promise. Okay. All right, you guys take a minute. I want you to find the dot product of these two vectors. All right. Everybody good? Need some more time? We get it? Everybody got something? All right. First off, let me ask you a question. Are there any answers on this multiple choice that you can get rid of right away without having to worry about it? A and B? Why? The units are wrong, correct. Right, remember, if you're going to multiply these together, it has to have meters squared, right? So A and B can't be the one. Okay. I've written out the long form of the dot product. Okay. I've written out the long form of the dot product. The nice thing about this is I think it's very cathartic to write it out this way because I get to cross out a lot of things. Because that's zero, that's zero, that's zero, that's zero, that's zero, that's zero. Right? Anything that is not I, J, J, and K, K is zero. Right? So what are we left with? -10 plus 10 plus 12. These are zero. Is 10 minus 10. Carry the 2. 12 meters squared. C. Okay. So, Dr. D, are you saying that a dot product is just multiplication of the I, J, and K terms? I am saying that to you right now. This is exactly what I'm telling you. Dr. D, what happens if I have two vectors that aren't defined in Cartesian and I'm taking the dot product of them? You won't. Like this is not how it's going to work. I'll be honest with you. Like, how am I going to report them to you, right? With an angle? Well, then what is the first thing you're going to do? Is you're going to create a Cartesian coordinate out of them and then just do this. So, right, like it's an extra step, but it's not. MATLAB will do a dot product for you if you like MATLAB. If you don't like MATLAB, it's so sad. MATLAB never did anything to you that I'm aware of. Anyway, the command for a dot product in MATLAB is dot, right? So if you are interested, if you were to say dot P comma Q, and obviously you have to define P and Q first. You just can't type dot P and Q and then it knows what you're doing. Okay, I know. It's until you get that Elon Musk Neuralink, it's going to be hard times, guys. Anyway, that's the command if you want MATLAB to do it for you. Okay. Okay. The green box returns. All rejoice. All hail the green box. Okay. Do we have time for this? I mean, we got like 5 minutes. I'm gonna call it for today. We'll do this next time. Oh, never mind. Wait. No, I'll just do it next time. It's fine. We'll go through it next time. See you guys on Thursday. Have a great rest of your day. I will try. If you download the Poll Everywhere app, it'll just keep track of the last one that you did also. Yeah, go into class, go to class resources, go down to mastering engine. Oh, go up where it says mastering engineering. No, that's the e-text. Go down, this one. Yep. There you go. That was easy. Thank you. Yeah, no problem. Guys, I will be working from home tomorrow because I have to bring my car in. So if you have questions and you need me, Discord message, okay? Or Halo. If you haven't started the homework, what are you waiting for? Start the homework. If you're waiting for an invitation, it's in the mail, I swear. But I would start it before that gets there for you. No problem, Kenton.
Every night before bed. So I couldn't just sit there and work on it.
What's up?
So I'm like, so I didn't like to do So I built my life around that day and I achieved the last week.
Yeah.
So I'm waiting for the price. Is there any way that I can make it up?
Talk to me next week. Let me think about that.
Okay.
So we'll discuss it later.
Thank you.
Yep.
It's not ideal, but I'm